Ready? Okay. Any questions? Hang on, everyone. Temper your enthusiasm. We have.
Did you fill out a bracket?
No.
No fun this time.
I'm a hockey fan. Any questions about anything?
Is it the same 4x4 panel though?
Okay. Rahul has a question. Question.
When is the test? What series? Like, what is the test going to cover? And where do we stop? Like,
What is the test going to cover, and where do we stop? Well, I mean, we haven't covered a lot on genetic algorithms in class, but you've done problems on them. I want you to understand how they function. You know, how the PC, PM, and all that stuff. I'm not expecting you to know the stuff we're going to talk about later on, like looking at them as Markov chains on population space. But that we haven't covered in class. Everything else that we covered in class through the end of Markov chains and Metropolis and Metropolis Hastings, you're responsible for. Okay. I would say the bulk of the test is going to be Markov chainy kind of stuff, Metropolis-y kind of stuff. Okay.
Chapter 2 from Mitchell's book, will that be covered in class?
No. Just this. What you need to know about genetic algorithms is just how the standard genetic algorithm functions with fitness proportional selection, PC, PM, all that stuff. Yes.
Are we allowed to bring your formula sheet?
No formula sheet. You don't need it. Calculator, fine. You won't, I hope. Although, you know, people have been saying, well, I went and used Wolfram Alpha to solve for the eigenvalues of this 2x2 matrix, and I'm like, come on. You know.
Who would do that?
3x3? You didn't have to. Anyway. Any other questions? You know, actually, let me just poll you guys, because I'm on the committee that deals with this kind of stuff. The new academic calendar this year. Oh, Rishi?
Well, I was playing around Boltzmann Alpha yesterday, and I encountered a symbol that looked like a pound sign.
Yes.
I was really confused what that was. It was like z equals the root something pound 1 to the 6th.
No. No. I use that as like a superscript for more Penrose pseudo-inverse. That's the only thing I ever use it for. What? What's so funny? You're hiding behind Mohammed. No, you don't care to share. Okay, that's fine. Okay, poll for you guys. New academic calendar. Goal was to mitigate this 8 uninterrupted weeks of classes before spring break, which we used to have. Used to have 8 solid weeks, then a week of spring break, then 6 solid weeks. And the old dean of the faculty decided that, which I think for good reason, that was stressful on students to have all that 8 dark, cold weeks in a row. And it would be good to have a break in the middle. Some big committee got together. They couldn't figure out a non-kludgy way to do it, so they did it a kludgy way. They gave you a 2-day break in February. They put it on President's Day weekend to be family friendly instead of halfway through. Okay, to me, the time up through next week to spring break seems longer. It doesn't feel like I've had any kind of a break between when we started and now. It feels just longer than it used to have 8 weeks of uninterrupted classes. Now, I'm not pushing you to say you agree with that. I'm just asking you. Did you, I mean, I know from Facebook that some of you had like nice ski trips and whatever for that 2-day break. You know, if you can afford a ski trip, that's great. If you can't afford a ski trip, bummer, you know. Some people had time to go out and have interviews in California, whatever, fine. But what do you think? Do you like this new calendar? Forget about the final exam stuff. Just this break, this 2-day break. No? Yeah, Trevor? Oh, well, the distance or the delta t from start of semester to real spring break is definitely longer. But there's a 2-day break in the middle to cut that.
I think that.
I mean, the thing that kind of is annoying is the spring break doesn't line up with any other university spring break.
Well, there's no universal spring break week, actually. Ithaca College, for example, always has theirs a week before our old time, you know, that kind of thing. So.
What I found is that, like, the original, like, right in the
It does. Yeah, agreed. Yeah. So you like to have it lined up with other colleges' spring breaks for what reason?
Just like your friends from home, being around at home while.
Okay, home. So it's not like every college kid in the U.S. is going to be in Cancun partying, and you want to be.
That's what he's
True.
saying. I think the February break in the middle messed up some professors' like schedules for what they're going to cover and when. So it ended up pushing a lot of things like this week and next week are busier than they had been in the
Yeah.
past. Fall break because fall break messed up our schedules and more stuff is shoved after fall break.
Yeah. Well, I mean, really, that's the professor's fault, and I mea culpa. I mean, I told you that the homeworks were messed up because of that, and in this class, but I don't think there's been a big, sort of shoving of work to right before spring break in this class. But there was a little bit of disconnect, yeah, with the order of Matt and Alex.
I think it kind of is a lot of work just now surrounding spring break because this week is really busy, and then coming back from spring break, I have like 3 weeks.
Mm-hmm.
That week right after.
Because that's like the 2/3 week now. Yeah.
Okay.
Okay.
Now I'm gonna study.
Yeah.
I feel like there's a dead stop.
You feel like what?
There's a dead stop in all 555.
Yeah.
I think the main thing is we're not stressed out at that part of the semester yet. It's very early, and there's not a lot of work. So it's like
Yeah. Okay. Well, that was this year. Like maybe 1 year President's Day weekend will be like 2 weeks later, and we'll. Yeah, I don't know. We'll see. Well, this calendar is undergoing a 3-year trial, which, if enough disasters happen, might be aborted. Okay, I'm not sure. And some of the disasters with final exam schedules are really crazy. Like since they're not doing it on the basis of class meeting time anymore, they're doing it on the basis of actual who's in what course to avoid conflicts and 3 and 24 and all that stuff. We've had people's 2 exams scheduled right on top of each other that many people were taking both classes. So, that's not a good thing. So, there's a lot of bugs. We're going to have to work it out. Okay, I don't want to spend any more time on this. I want to get back to genetic algorithms, which is what we were talking about last time, unless there are further questions. I have graded homeworks 1 here that you can pick up. And by the way, if your name is Michael Wang, W-A-N-G, there's 2 of you in the class, and so we don't know which one of these is yours, and so you're going to have to start putting your net ID on. Okay. Okay, so we're talking about the standard genetic algorithm. And last time I went over just the basic framework. So P of t is the population at time t, and also sometimes people call t the generation. After t generations, this is what the population is. It has fixed size n, and the individuals in P of t are L-bit strings, and in the background you have some set phi, which is like phenotype space, which is the set of candidate solutions to some problem. And you have this function f from phi to the reals. F is always strictly positive, and that's something that measures how well a given phi in capital Phi solves the problem. And you have this encoding function g from the set of all L-bit strings to phi. That's surjective. And for those of you who didn't take EC 3050 surjective, all that means is that everything in phi gets encoded by some L-bit string in the set of all L-bit strings. And this is the encoding. And for x, an L-bit string, by sort of abusive notation, we let phi of f of x be f of g of x. So the abuse of notation or misuse. And f of x is the fitness of x. And last time I talked about how you, once you have parents for the next population, how you generate the offspring. So we discussed, and by the way, n is even throughout this discussion. We discussed how, once you have n parents for p of t plus 1, selected somehow, and that's what we're going to talk about for the most part today, from p of t, you generate offspring. So this is the way you do this is you pair up the parents, and each pair gives rise to 2 offspring who become members of p of t plus 1, and we have this crossover and mutation, various kinds of crossover, various kinds of mutation, and all that kind of stuff. So we talked about that last time. Now what I want to do is I want to talk about this somehow. I want to talk about how you select the parents for the population of time t plus 1 from the population of time t. So, question, how do we select parents? There's various ways of doing that. And the one that Mitchell's book talks about the most, and the one we're going to devote the most time talking about, and the one that Holland, the originator of genetic algorithms, used the most, and his followers, is what's called fitness proportional selection. So there's many ways to do this, and I'm just going to outline a few. So the first way is what I call fitness proportional selection. And how does this work? I'll give more details later. And the book sometimes, I think, says fitness proportionate, sometimes fitness proportional. I just settle on fitness proportional. I don't know. What you do is you go through and you select the n parents from p of t. And remember, you have to select n parents, then you pair them up, and each of them gives rise to 2 offspring. So that by drawing from p of t with replacement, and if you haven't ever taken the probability course, just think of a bin full of different colored balls, and you reach in the bin and you pull out a ball at random and you record what that was, and then you throw it back in the bin. That's replacing. And then you make the next draw. So you're drawing with replacement. Wait. Were you here last time? No.
I'm not in the class.
Yeah, okay. I was thinking. Skipping embedded systems. Oh my God. Jose Martinez. Well, actually, we're both on video note, right? For those of you taking 3140. Okay, who happen to be watching this lecture. Okay, so you draw from p of t with replacement in the following fashion. So that if x in p of t is any individual, the probability of selecting x on any of these draws is proportional to the fitness of x. So on any of these draws, you're going to draw an individual out of the population with higher probability if that individual has higher fitness, and lower if it has lower fitness. And we're going to see the details a little later on. We'll find out that there's actually only one way to do this, et cetera, et cetera, et cetera. Okay, so that's one way to do it. Another way to do it is tournament selection of various kinds. Okay, how does tournament selection work? you do the following n times to get the parents. And this is just one example of tournament selection. There's other kinds as well. You choose q less than n individuals uniformly at random from P of t. And after you've done that, you take the highest fitness individual out of those q. So out of those, you take the highest individual, the highest fitness individual, a parent for P of t plus 1. And then you throw those q individuals back into the population and repeat. So you go through this process n time. You have n tournaments consisting of q competitors, and you could fill out a bracket for that. You know, if you, since it's March, we're supposed to be filling out brackets. Max wants to know if I fill out a bracket. I said no, because I'm a hockey fan. It's easier in hockey because the 16 teams that go to the NCAAs, you're already Sweet 16. You know, there's no like this, that, now you're Sweet 16. Less random excitement, right. The office pools aren't as big. Okay, so that's another way to do it. And there's other ways. There's elitist selection of various kinds. For example, and I'll give you two kinds of elitist selection. It turns out these are the ones that people actually use most of the time in applications, and we'll get to that, why they do that later on. The kind of the half-full elitist selection goes like this. You skim off the top of the population P of t, and you throw those in. You sort of seed population at type t plus 1 with those best individuals. So take, say, the top 10% fitness-wise individuals in P of t, and you start P of t plus 1 off with them. So throw them right away into P of t plus 1. You don't even make them reproduce. You don't make them do anything. You just throw them right in, unadulterated. And then you fill out the rest of P of t plus 1 by, for example, fitness proportional selection. Okay? And you might even reuse those individuals as part of the fitness proportional selection scheme. So even though you favored them by throwing them into P of t plus 1 to start with, you might end up having more of them arise through the fitness proportional selection process. So that's one way to do it. Or, and here's the half-empty version, of elitist selection. Or you throw out the bottom 10%, say, of P of t, and you forget about them, and you use fitness proportional selection, for example, to fill out P of t plus 1 from the top 90%. Now, we could get into a nice, sort of political analogy here that the half-full version of elitist selection is like affirmative action or something, and this is like racism or something. You throw out the bottom 10%, but I won't go there. I'll only crack the door open so you can groan or roll your eyes or whatever you do when I do stuff like that. Okay, another one, just the last one I want to talk about, is Boltzmann type selection. And this is kind of like fitness proportional selection, except you don't determine the probability of choosing a given individual just by picking it with a probability proportional to its fitness. Okay, so this is like fitness proportional, but you draw an individual X on any of the n draws with a probability that looks like this. And when I write it down, you'll see why they call it Boltzmann selection. E to the sum number alpha times f of x divided by the sum over y in p of t, e to the alpha f of y. And here alpha bigger than 0 is some parameter. It's a user choice. Now, why would anyone ever want to do this? Well, this is kind of like an adjustable sort of selection mechanism. It turns out that, and it's pretty easy to show, and this is going to be a future homework problem, that higher alpha implies higher, what people like to call selection pressure. That is to say, higher alpha means that you treat high fitness individuals more favorably than you do when you have a lower alpha. And you can sort of see that, like if you let alpha go to infinity, everything except the absolute highest individuals has a vanishingly small probability of being selected. And this makes you think, well, wait, maybe I could design this evolutionary algorithm intelligently by, say, start out with a low alpha, and then when I get better and better populations, ratchet alpha up, increase selection pressure, that kind of thing. Okay, so this makes you think, so perhaps you could start with a lowish alpha and increase it later. Why not? It's kind of like the simulated annealing thing. You know, you start out with a relatively high temperature and you lower the temperature as time goes on, and what that means is you're being more, you're prejudicing your simulated annealing, your metropolis steps in that to be more around the spikes in the E function. Okay, but let me just tie this back to the metropolis a little bit, tie this back to the metropolis simulated annealing stuff. Note that as in metropolis, the random aspect to the selection means that you're always going to maybe select low fitness individuals to be parents of the next generation. So as in metropolis, the selective randomness allows for lower fitness individuals to sort of participate. They don't get sort of cut out of the process, except perhaps for that half-empty version of elitist. And the reason you want to do that is because you want to make sure that it might be true that you get to higher fitness individuals by moving through spaces of lower fitness individuals. So the lower fitness individuals, quote unquote, participate. In other words, the route to high fitness might go through lower fitness, broadly speaking. And once again, we have this exploitation versus exploration. being able to choose lower fitness individuals for parents allows us to explore more of this phenotype space. Rahul, you had your hand up.
Is that f of alpha, gamma on top, or is that
F of x. F of x.
At the bottom, f of gamma, right?
F of y. Yep.
And alpha means, if alpha is high, that means you'll be more favorable towards the higher.
Yeah, yeah. Yeah, well, it's going to be a homework problem. You'll see exactly how it works out. But intuitively, what's going on is, for a very high alpha, all the terms in this sum down here, except when y is the same as the highest fitness x, get swamped. And so the probability of choosing a very low fitness x is small. That's the basic idea. All right, so those are just some of the kinds of selection methods people use. And let's look at a closely at fitness proportional selection. Because that's what, for example, Mitchell's book talks about the most, and that's the one that Holland settled on and all his disciples. All right, so what is fitness proportional selection again? You draw n parents for the next population, and for a given x, in P of t, what I want to define P sub cell of x, P select of x, equals the probability that you select individual x on a given parental draw. You make n such draws, and on each of those draws you make the same way, with the same probability distribution over P of t. Now we want, for all x in P of t, P cell of x is proportional to f of x. That is to say, what do I mean by that? I mean that for some fixed constant, call it C0, positive constant C0, P cell of x is equal to C0 f of x for all x in P of t. So there's the same proportionality constant for everybody, and we want that equation down there to hold. And as it happens, there's only one way to do this. There's only one C0 that works. So here's the fact. And I just like to say there's only one way to do this, to make this happen. And that goes like this. P cell of x is equal to the fitness of x divided by the sum over all y in P of t of the fitness of y. And note the kind of orthographic resemblance of this formula to that Boltzmann formula, except now you've got terms that are linear in the fitness rather than exponential. Orthographic? Oh, it's just a highfalutin word. You know, orthographic means essentially the standards of writing. Okay, so you know, ortho means right, like orthodox, that kind of thing, right? Graphic means about writing. So, like for example, the orthography of the 16th century might have called for all words that begin with a J to have an S at the end, something like that, whereas it doesn't now. Probably a better word in this context would have been the morphological similarity between. You nod vigorously.
So you're just messing with us with big words.
So I was just messing with you with big words before. Well, morphologically is bigger than orthographic.
Well, I know what that means.
Okay, cool. Well, anyway. All right, so why is this the case? Why is it true that the only way to make everybody's P cell proportional to his fitness is by setting P cell equal to that? Well, the reason is that all these probabilities, we need that the sum of x and P of t of P cell of x to to be 1, because every time you pick a parent, one of these draws with replacement, you're picking according to some probability distribution that assigns probability p cell of x to every x. The sum of those has to be 1 for it to be a probability distribution, which means that the sum of x in p of t, c0 f of x, has to be 1, which means that c0 has to be 1 over the sum of all x in p of t of f of x, which is the same as the sum over all y in p of t of f of y, because x and y are just dummy variables of summation. Okay. So fitness proportional selection is that probability of choosing any x. Now Goldberg, David Goldberg, whose name I'll refer to on several occasions, he was a graduate student of John Holland's, and he went on to be a faculty member at Georgia Tech and University of Illinois. And then he started a company, made a lot of money, and retired. So anyway, and he also wrote the first book on genetic algorithms, per se, called Genetic Algorithms in Search Optimization of Machine Learning. I'll have some interesting things to say about that later on. But Goldberg, student of Holland, gave us sort of a useful kind of physical analogy to fitness proportional selection. He called it roulette wheel selection. How come? Well, here's the idea. What you do is you take a roulette wheel, right? And you assign each individual in the population a wedge on that roulette wheel. And the ratio of the wedge's area or arc length or whatever to the total area or arc length or whatever of the roulette wheel is equal to that, f of x over the sum of all the fitnesses y. So the idea here is that each x in p of t is allotted a quote-unquote wedge on a roulette wheel, and the fraction of the area is equal to f of x over the sum over y in p of t f of y. And you spin the wheel, hopefully with a marble on it, every time you pick an x to be a parent. So you spin the wheel n times to select n parents. And the wheel doesn't change, which embodies the whole with replacement thing. Okay. Once you've selected an x, it's still got its wedge on the wheel. It's still eligible to be selected again on a subsequent draw. Rahul?
Are these wedges, with the size of the wedges determined by the fitness of the particular x?
Yes. Each x is allotted a wedge on the wheel. The fraction of the total area of the wedge is this.
Which is the fitness, right?
F of x, the fitness of x, divided by the sum of the fitnesses of everybody in the population. Yep.
Is p select based depending on time?
No.
It's not. How come then we have the sum over p of t?
Because every time you have a population, you want to pick from that particular population. Oh, well, yeah, in that sense it is dependent on time. But the scheme for calculating it is not.
Okay. But so then the probability does change, right, within each.
Yeah. Like if you have, when the population changes, the denominator changes. You know, in fact, you might have a completely different population of completely different strings from p of t and p of t plus 1. So, yeah. Okay. So anyway, that's a summary of roulette wheel or fitness proportional selection, how it works. And so here's a question. Suppose we're using fitness proportional selection. What is the expected number? So given x in p of t, some individual, some specific individual, what is the expected number of times that x appears as a parent for the next generation, p of t plus 1. Remember, we draw n parents. So we have this list of parents. All those parents are going to be strings from p of t. So every one of those parents is some x in p of t. Given some specific x in p of t, what is the expected number of times x appears as a parent for p of t plus 1? Matt?
N times p cell of x.
Yes, that's exactly what it's going to be. So here's the answer. That is n times p cell of x. Now let me just explain why. Okay, it's easy. I want to show you a useful argument technique for a situation like this. So here's a kind of a quote-unquote neat proof. Okay, I want to define a 0, 1 random variable, actually a sequence of 0, 1 random variables, z1 through zn. So define the random variables z1, z2 up through zn to be IID. Well, they will be IID. So I want to define them as follows. Zi is equal to 1 if you draw x on draw I, and 0 if you don't. Okay, and this is for 1 less than or equal to I, less than or equal to n. You're drawing I parents, so you do that I times. The z's are IID, and the probability of zi equaling 1 on any for any I is equal to p cell of x. For all I. And you can write the expected value we're trying to calculate as the sum over I of the zi's, the expected value of that. So furthermore, and if you've actually read the Markov chain handout, you saw that I use an argument of this kind to give a formula for nj of n in terms of the transition probability matrix. Does that ring a bell for anybody? Or haven't you penetrated the handout that deeply? Yes, Rahul? Good. Trying is where everything starts with trying. Seriously. That's right. A lot of things end with a 2. Was Max's word of wisdom there? Okay, for those of you watching at home who can't hear. We ought to give some of you mics because you talk so much. All right, so furthermore, the expected number of times x appears in the list of parents, and I think it behooves me just to write this out instead of inventing some notation on it, is going to be the sum from I equals 1 to n of e of zi. And e of zi is always equal to p cell of x times 1 plus 1 minus p cell of x times 0, because z takes on value 1 with probability p cell of x, 0 with probability 1 minus p cell of x, and lo and behold, you sum n copies of p cell of x, and as Matt said, you get n p cell of x. Okay? Now, there's another way of looking at this. So note that you can write np cell of x as follows. It's going to be f of x divided by 1 over n times the sum from over y in p of t, f of y. All I did was I took our formula for p cell of x, put an n in front of it, but I ported the n to the denominator by turning it into a 1 over n. So this is the same as the fitness of x divided by the average fitness of individuals in p of t. So what does this tell us? This tells us that if, and in fact if and only if, an individual has higher than average fitness, we expect to see at least one of him among the parents. Because n p cell of x is then bigger than or equal to 1. So thus, qualitatively, we expect to see at least one x among the parents for p of t plus 1 if and only if f of x is higher than the average fitness of individuals in P of t, where the average, I just mean the mean, the 1 over n times the sum of them. Okay, so that's a kind of a qualitative thing that you can say. All right? Now, what if, for example, what if there are m copies of the same string in P of t? So what if there are m copies of some specific string in P of t? What is the expected number of times you expect to see that string among the parents for P of t plus 1? So this is easy to show. The expected number of times that string appears in the list of parents for P of t plus 1 turns out to equal m times that number there. M times f of x divided by 1 over n sum from sum over y in P of t, f of y, where x is any individual instantiation, is for you, Max, of that string in P of t. I've been using x to denote individuals. But anyway. So what does that say? That says that I just heard something that threw my train of thought off. It was cool. It was a nice little blip, but I won't even look and see where it came from. If you have m copies that you expect to see, if a string has higher than average fitness, then you expect to see at least as many copies of it in the list of parents for P of t plus 1 as there are copies of it in P of t. So thus, that if a string, it's an if and only if, so I'll write it that way, a string has higher than average with respect to P of t fitness, that's going to be equivalent to our expecting to see at least as many copies of it in the list of parents for P of t plus 1 as are in P of t. There's m copies of it in P of t. Then we expect to see at least m of them. We may not, but we expect. That's the expected value. Okay? All right. Now you can generalize this. as follows. And you get something that I've given a grandiose name that it doesn't deserve, the subset selection lemma. And it goes like this. If Q is any subset of P of T, so let Q be any subset of P of T, the expected number of times you expect, no, the expected number of appearances of individuals in Q in the list of parents for P of T plus 1 so the expected number of members of Q, and when I talk about members of Q, I mean individuals, so there could be repetitions of the same string if Q has 2 versions of the same string, so on, that appear in the list of parents for P of T plus 1 is given by the following formula. It's a variation on this. It's the size of Q. This is notation for the size of a set. I'll write that down at the bottom of the word in a second. Times the sum over y in Q of f of y divided by the sum 1 over n times the sum over y in P of T f of y. Or actually, no, the Q, I'm introducing this too early. It's equal to that. It's equal to that. Okay? And you can just use the same kind of argument, the 0, 1 kind of argument. You let zi be 1 if an element of Q is chosen, and so on, that kind of thing. Now, we can rewrite this as follows. This is equal to the size of Q times the following ratio. And there's a handout that proves this, by the way, the handout on the schema theorem. If you introduce a factor of the size of Q, so Q absolute value is the number of individuals in Q, the reason I wrote it that way was that that last formula tells us what? It tells us that if the set Q has higher average fitness than the whole population does, then among the parents for the next population, we expect to see at least as many elements of Q as there were elements of Q in population P of T. Yeah, go ahead, ask.
Okay, so in this case, let's say you have Q individuals, right? Giving the subset selection lemma that you have, you're taking that Q individuals from population of P into population of P plus 1, right? My question is, will the expected, like, will the fitness change from population to population?
The fitness of a string is always the same forever and ever.
But the average fitness of the population, will that change?
Yeah, sure. Oh, absolutely. That's a population-dependent quantity. The average fitness of the population will change over time. In fact, that might be the thing you're tracking. That might be an F you use in, say, ergodic theorem for Markov chains. You know.
So basically, you could have, like in this case, X that is occurring so many number of times in P of T, and you do it in P of T plus 1, but because the average fitness grows up, it might not carry on to FT plus 2, right?
Well, the average fitness doesn't have to go up. It might go down even.
Right.
But the whole point is that the populations are evolving randomly. You know, if you use fitness proportional selection, it's possible to select, for example, the same string for every parent if you're lucky or unlucky. And then the crossover is not going to help, and mutation is the only thing that's going to do anything. You know what I mean? Like,
Yeah.
it's totally random. You know, and we've seen. You know, you learned on homework 2, I think it was homework 2, that the number of populations of size n consisting of L-bit strings is astronomical, right? It's like 2 to the L plus n minus 1, choose 2 to the L minus 1, or choose n. It's huge. So you're never going to explore the whole population space. You're only going to explore a small fraction of it. Okay, so but let me write down what this means. So, thus, if the subset Q has higher average fitness than the whole population, then, and in fact, this is an if and only if, you expect to see at least size of Q, individuals from Q, in the list of parents for P of T plus 1. Okay? All right. Now, why am I going through all this? Well, you've all read about the schema theorem. And I'm going to and actually let me just give you a little caution here. So this whole thing is kind of the beginning of a talk about the schema theorem. So the subset selection lemma is essentially the foundation for it. It's related to Holland's schema theorem. Now, I'll talk about the schema theorem specifically in a moment, but I want to warn you right now that, in my opinion, Mitchell's argument, and she just essentially reproduced Holland's argument for the schema theorem, is sketchy. The math is sketchy because she mixes up expected values and probabilities in a weird way. Essentially, what she does is she takes the formula for the expected number of times members of a schema appear and then multiplies it by probabilities. So she's got probabilities multiplying expectations. Not quite kosher, okay? So let me just say, Mitchell's proof is, in my opinion, and I apologize, Melanie Mitchell, if you're watching this. You know, she's a very nice person, by the way. She teaches at Portland State. I think I might have mentioned that to you. Sketchy. Okay. It's sketchy, and the handout I just put up the other day, it gives an airtight proof, a better proof, a more methodical proof. Well, let's just say better. It's better. And in fact, it gives a better lower bound. Yields a stronger result because I'm a little more careful about keeping track of things than she is. Okay, so brag, whatever. All right, so we'll get to that in a second. Now's a good time to take a 3-minute break. And if you are Michael Wang, or Wang, however you say it, one of you, please come up. If not, we have to settle who you are. Okay. What's that? Not here. Yeah, me. The schema theorem, I'm not going to write down the formulas for it and everything. I'm just going to tell you the idea of it and then criticize how it's been used and give some illustrations that show from the literature that show sort of how people's wishful thinking took over and then how people figured out that that was wrong and all that kind of stuff. But I think it's really useful to think through these issues because then when you're actually, you know, there's still people who think this is how genetic algorithms work. and whatever. If you're ever using them, you'll know to watch out for some of these things. But anyway, does everyone understand the schema concept? You've read about it, you've worked homework problems on it, and all that kind of thing. So I don't have to go over that in class. I'm just wondering. Matt?
Are you asking things beyond like what is a schema?
Yeah, what is a schema? That's all I'm asking. You get that?
Yeah.
You get that. A schema is essentially a special kind of queue, a special kind of, or it's a special subset of strings. It has a defining symbol that has zeros, ones, and stars in it. Stars are like anything, just like Unix. You know, if you type rm star, you know that's not good. Yeah, right. You did that once, Randy?
I did that. Do you know Nomen?
Do I know who?
Nomen Pi. I actually
Familiar.
I accidentally did something where I did like an rm-rf and I used the wild card.
Oh no.
Oh.
RM-RF slash.
Can you just type undo after?
No, you go to the system people and say, I need the backup from yesterday. You know, like that's what you. Okay. So anyway, we all know what a schema is. We've quote unquote studied schemas. Okay. And what the schema theorem does, it applies essentially. It's related to the subset selection lemma. The schema theorem addresses the situation where Q is equal to the intersection of some schema called H. H is the generic schema letter that everybody uses. Does anyone know why you use H for schema? Transfer function? Dude. No. This is only my theory, okay? It's only my theory. Okay, well, I'll let you think about it for a second. That is to say, Q is the set of all representatives of H that are in P of T. Okay, let me tell you what I think H stands for. Hyperplane. That's what you're thinking too. I know. I knew it. Okay, so let me just give you. Here's an example. For example, suppose P of T is equal to. Suppose L equals 2 and P of T, or L equals 3 and P of T is 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0. And H is 1 star 1. What does H intersect P of T? No. What if H is 1 star star? I just want to make sure you all know what schemas are. It's all these guys, right? Okay. Good. All right. So you know what schemas are. So anyway, the schema theorem addresses that situation. And what it does is it establishes a lower bound on the number of H representatives, not in the list of parents for P of T plus 1, but actually in P of T plus 1. So the theorem establishes a lower bound on the expected, italics mine, number of H reps in P of T plus 1. Note, not in the list of parents for P of T plus 1. The subset selection lemma addresses the expected number of representatives of some subset Q among the list of parents for P of t plus 1, not in P of t plus 1. Schema theorem goes for the jugular, establishes a lower bound on the expected number of H reps in P of t plus 1. Okay, now what does this lower bound consist of? So the lower bound depends on various things. It depends on a formula much like the one we saw in the subset selection lemma. So a formula much like the subset selection lemma for Q intersect P of t, or Q equals H intersect P of t. And it also depends on PC and PM, the mutation and crossover probabilities. And it depends on the number of defined bits in the schema, O of H. And interestingly, we're using this, or I'm using this pound sign a whole lot today, you know, after, maybe you just got it in my head. Yeah, okay. Number of defined bits in the schema H. And it also involves a term that talks about the defining length of H. And what is the defining length of H? That's going to be the, if you take the leftmost defined bit and the rightmost defined bit and count the number of interbit interstices en route from one to the other, that's the defining length. So it's the quote-unquote distance between the left and rightmost defined bits in H. Okay, so the schema theorem involves formulas for all these things. Why do these PCPM, O of H, and defining length come in? Well, they come in because once you have an idea of roughly how many guys in H intersect P of t are among the parents, then you have to assess the probability that they get ripped apart by crossover or mutated out of H by mutation, that kind of thing. And that's what the schema theorem does. Alex? Not wildcard bits, right. Yep. All right. So anyway, there's this formula. Now, as I said, if you look at the handout, you'll get a better formula. And you could even make it better if you think about it. Okay. So I hereby challenge you to do that. I'll let you do it because you're not in the class and you like math. Okay. If you want, I'll make you a guest on the website. All right? Send me an email. You had your hand up.
So there can be a defined bit right at the center, right, in between the leftmost and the rightmost.
Yes.
But that wouldn't be considered
the leftmost or the rightmost.
Right, but then I'm guessing that this is because of the fact that when two parents, either crossover or something, we'll be using this term, right?
Yeah, the idea is, say you have, say the schema has a 1 at its left end and a 0 at its right end, say, something like that. And the idea here is that if you're if one of your if this can cross, let's not make it this way. Let's make it this way. It doesn't matter what this guy is. It could be 1, 3 or whatever, 1 0 1 1 1, something like that. If you cross over here, then one of the crossover products is still going to be in that schema. That's the point. So if you cross over in here, though, neither of the crossover products will be in the schema. So that's what the theorem looks at stuff like that. But read the handout, look at the handout, and see if you like my argument as much as I do. Just kidding. All right, half kidding. Anyway, so the schema theorem does this. It gives you a lower bound on the number of guys in H intersect P of T that you expect to see, and remember this is only an expected value, it's possible that you don't see any, no matter what, just by virtue of the way things are selected, that you expect to see in P of T plus 1. Okay? Now, there's nothing wrong with the schema theorem. Okay? So this is important. This philosophical thing is important. There's nothing wrong with the schema theorem. What's wrong is how it's been overinterpreted and misapplied over the years. So what's wrong is how it's been overinterpreted and misapplied. I can't emphasize this enough. Over the years, to quote-unquote explain why / how GAs work. Okay, that's what's wrong. Okay, now we don't have enough time to go into this in depth today, but the whole thing, the way that Holland was thinking was as follows. So Holland's original line of thought. Went like this. And this is sort of based on biology. That what happens in biological evolution, okay, so bioevolution, by means of crossover and mutation, various kinds, assembles genotypes that work well. And how does it do this? Well, it finds small clusters of nucleotides that when they appear in a row and encode a protein or whatever, make a useful protein. Okay. So intuitively speaking, since we're only 1 minute from the end, I'll just say it, and next time I'll go over it on the board. Okay, biological evolution assembles genotypes that work well. What does it mean to work well? It means that you encode a lot of useful proteins, right? So how do you build a genotype that encodes a lot of useful proteins? I'm being very, by the way, cartoonish and sketchy about biological evolution here. I'm ignoring all the development and all that kind of stuff. You find a little piece, a little sequence of nucleotides that encodes for one useful protein. And then you have an organism that has that. And another organism that mates with it has another little sequence of nucleotides that encodes for another protein. They mate, they cross over, boom, you have an organism that encodes for both. See? So little pieces, little segments of the genome get combined by crossover to make a big genome that encodes a lot of proteins. And he was hoping that what these genetic algorithms would do would find little segments of zeros and ones that together did something good, and populations consisting of strings with those little segments in place would proliferate, and there would be other little strings, and then they would cross over and they would go together, and he called that the building block hypothesis. And the problem is the math. The math is sketchy. The math doesn't work, and I'll try to explain that next time and give you some examples from the literature that illustrate it. Yeah.
When you're finding the length of H, what if H is star 1 star? Is the length 0 or 1?
Star 1 star. It's length 0. Yeah.